Hello folks, this is Mr. Rob. Once again, we are going to do the scientific method, a brief lesson on the material that was covered in class during the first week of September. This is all information that is found in our textbook, Holt Physics. Here we go. So the scientific method is nothing more than a process. It's a series of steps that we follow so that our information, any event actually, let's broaden this view. Any event that we observe can have this scientific method applied to it in order to come up with a solution. And so really the process is observe an issue, an event, make a hypothesis, and present a solution. So let's work through the steps. We make initial observations and collect data that leads to a question. And the kind of questions that are usually asked by this very first step are, why did that happen? How did that happen? What caused that to affect the other thing? Things, all the things. Here we go. Second step is to formulate and objectively test our hypotheses by experiment. And I'll explain a little more on how we do that. But what it means is that we create or formulate and objectively test. By objectively, we are saying without bias. That means we are not looking for a specific answer, we are looking for all potential answers, and our tests reflect that. Alright, so we do experiments or tests, and they help us to explore how our hypothesis really applies to the situation. And we do this sort of testing by using a model. I'll explain that shortly. We use a model in order to formulate and objectively test hypotheses. After we've done our tests, we must interpret our results and revise the hypothesis if necessary. In other words, if we come up with a result that did not answer the question that we asked or the hypothesis that we had created, then we must either go back, reformulate, and retest, or if it does, we move on to the last step, which is to state conclusions in a form that can be evaluated by others. In the scientific community, all research must be peer-reviewed. In other words, when they create their hypothesis and do their experiments, and they analyze their results and interpret their information, they then have to have that work published and reviewed by their peers so that it can be validated. In the scientific community, just to do something by yourself and to say the sky is green because I say it is doesn't hold any weight. You must collect data, you must show your test, you must show what you did to get to that result, and others must say, oh, I follow your logic. Okay, that makes sense. The sky is green. Well, we know it's really not, but just the same, others have to be able to evaluate it. Alright, so I mentioned model. Here we go. Physics uses models and systems. In order to apply our objective tests, physics and most sciences will use what is referred to as the system and model. And they use this to represent the problem or event. Alright, so the system means everything that's involved in the event, everything that could possibly affect what is happening. The model, however, is the part that only includes the relevant information, the stuff that really is involved, as opposed to the broader picture which encompasses everything. And although the parts of the model that has parts will be part of the system, the system is everything and the model is only the relevant stuff. We use models not only to help build, but to also objectively test our hypothesis. Some of our models can be visual or tactile. In other words, it's stuff that we can build and show representative, while others can be hypothetical. We use heavy mathematical formulas to approximate an event. And that's sort of the vision that we have for models and systems. So our model is something that we use to represent the initial event, because the model is something that we can deal with without having to deal with all of the objects in the system. We can narrow that down to just the relevant parts, and we call that our model. Here's an example. Upper right hand corner, an event which caused a question. So here I'm watching basketball, and I wonder, why do pro basketball players make it look so easy? My hypothesis: well, pro basketball players make it easy because they know how to apply physics every time they make a shot. No. System. All right, so I'm going to use a system and a model to help test my hypothesis. All right, so my system includes the basketball court, the player, the basketball, the arena, air pressure, weather conditions, types of sneakers. It could be any number of issues. But my model will include only the mass of the basketball, the height of the target, and the basketball's initial velocity. Because all I'm concerned with is how that basketball gets from the hands to the basket so easily. To objectively test my hypothesis, I might ask several pro basketball players why it looks so easy. Suppose that after asking 10 different players from 10 different teams. Not statistically significant, but for the purposes of this test, I think it'll apply. I find that only common answer is practice, lots and lots of practice. I realize that my initial hypothesis was incorrect. I return to my hypothesis, rewrite it, so it now states pro basketballs make it easy because they practice shooting a lot. Now I'm ready to make my report, and while in this simplistic case I'm the only one who needs to know why that is, in a real life situation you might be reporting to your boss or directly to a government agency if you're one of the businesses that's regulated and has to submit annual or quarterly reports. Never omit data. It is considered a solid scientific ethic to report all of your findings and hypotheses, even if they're wrong. Instead, offer your best opinion or best guess as to why your data was different from what you expected and how you altered your retest to change the results. Okay, that's all I got for today. We will be doing a couple of activities. We did the paper helicopters, and we're doing some measurement exercises today and tomorrow. See you in class.